So let's do an example that hopefully will make these concepts of the scattering matrix and how to determine them more concrete and clear in your mind. We're going to have a two-port device, or a simple two-port device, again consisting of a lumped impedance. In this case, instead of being a series, we have a shunt impedance. And this value happens to have a impedance that's numerically equal to twice the characteristic impedance Z0, the transmission lines connected to it. So these are 50 ohm transmission lines. This would be a 100 ohm resistor, this shunt element here. All right, let's go through and try to figure out what the scattering matrix is for this two-port device. So 4 scattering parameters, a 2x2 matrix we need to determine there. The first thing that we need to do, and again this is important, sometimes students will stumble right here at the beginning, is we have to set up our experiment. Let's say we want to go through and figure out the first column of the scattering matrix. In other words, we want to figure out S11 and S21. To do so, we need to make sure that there's an incident wave propagating down toward port 1. But there's an incident wave only on port 1. We need to make sure there's no incident wave coming in on port 2. So that's the experiment. We have an incident wave coming in onto port 1, no incident wave on port 2. We result in a scattered wave coming out of port 1, and likewise a scattered wave out of port 2. And that's what we seek. What are those two scattered waves in terms of the lone incident wave on port 1? There are many ways to approach this problem and find the solution then, and we're going to do it two ways in this example. We're going to use one where we do more the traditional way with telegrapher equations and boundary conditions, and then we're going to redo the analysis where we apply match sources and match loads. And of course, we'll end up with the same result in either case, since every valid method is valid. So let's start with a more traditional route. We're going to go through, and we know the telegrapher equations on the transmission line at port 1, and we know the solution to the telegrapher equations for the transmission line at port 2. Here, though, we know that we've placed a match load at the end of that transmission line. We are going to go and therefore make V02 plus equal to 0. In other words, there is no incident wave on port 2, and our total voltage along that transmission line consists therefore of simply the minus wave voltage, the scattered wave voltage, and we know from telegrapher equations what its solution is, what its form is. Notice it's e to the plus j beta Z2. Current, total current, then, we get from telegrapher equations for the left side where the port 1 is, and for the right side where port 2 is, and this is simpler because we only have, again, a scattered wave on that second transmission line. Be careful about the signs when you go through and do that. When the plus wave goes away, we still have a minus sign here in our current solutions. All right, so we set everything up properly, and now we need to do the analysis. Again, this is more of the traditional use the telegrapher equation, apply boundary condition approach. So ultimately what we're trying to find is the wave amplitude V01 minus, the scattered wave from port 1, and the wave amplitude VZ02 minus, the scattered wave from port 2. In both cases in terms of the one lone incident wave on port 1, so in terms of V01 plus. So again, we're trying to find these two values in terms of this one. We've done this before back in Chapter 9 more than one time. All right, we're going to do this by applying boundary conditions, and so we need to evaluate the voltages and current at the port plane. So we're going to go through and determine the total voltage V1 at the port plane of port 1, and we've defined that as location Z is equal to 0. And so our total voltage simplifies to this. All the complex exponentials turn into 1s when we value it there at 0. Same thing for the total current there at port 1, and then the total voltage and total current at port 2. Make sure that you know which direction these currents are pointing, or positive current is pointing. They're pointing into the port in both cases. Now we're going to apply boundary conditions. So our first boundary condition comes from KVL, and it's pretty straightforward when we go through and look at this structure. Because this is a shunt impedance, we find the voltage from the top conductor to the bottom conductor is the voltage, regardless of how we define it. And so the voltage at the end of this line at Z1 is equal to 0 must be equal to the voltage across this resistor, and that must be equal to the voltage at the beginning of this second line. Total voltage evaluated at Z Z2 is equal to 0. So this is our first statement here, and really the useful part of it from a boundary condition is the first equality. The total voltage V1 at the port plane is equal to the total voltage V2 at its port plane. Go through for a second boundary condition, and now we use Ohm's law along with KCL. And so we have our currents here and here, and we can see that these two currents, when added together, must be equal to the current IR. But that current IR is simply the voltage VR divided by 2Z0. And I probably should have put the step in here. This VR, of course, now is equal to either one of these voltages. So what if I did a little more algebra, I probably should have shown that the I1 plus I2 is equal to, let's say, V1, we put it in here, divided by 2Z0. That gives us our second equation. These are the boundary conditions, but again, we can apply a little algebra to simplify this situation. We earlier evaluated the port voltages and currents, V1, V2, I1, and I2, and now we can insert those into our boundary condition results on the previous page and do a little algebra, and we come up then with two equations and essentially two unknowns. The two unknowns are the minus wave amplitudes. Again, we're trying to solve them for them in terms of this plus wave, this incident amplitude V01 plus. So a little more algebra, we can get those two solutions, the V01 minus, the amplitude of the scattered wave at the first port, and V02 minus the complex wave amplitude of the scattered wave at the second. From these wave amplitudes, we can then determine the value of the scattered waves when evaluated at the port plane, where the index is equal to 0. And again, they're terms of the incident wave. Now, I've made a typo here. I have V1 minus. That should be a plus right there, and that should be a plus, V1 plus, the incident wave. So the scattered waves are in terms of the single incident wave. Now that we have these values of the scattered waves, V1 minus and V2 minus, when evaluated at the port plane, again, a complex number, we can insert them into our definitions for our scattering parameters in terms of the normalized wave amplitudes A and B. Insert them in there and do a little algebra, and we get S11 is equal to minus 0.2 and S21 is equal to 0.8. Now let's use an alternative method to evaluate the scattering parameters S11 and S21, and we'll show, since this method is valid, we'll get the same answer once again. Instead of using, as we did previously, the telegrapher equation solutions and applying boundary condition in a very classical method, instead we're going to attach a match load to port 2 and a match source to port 1. So we're going to set up our scattering parameter experiment for column 1 in this manner, with a match source and a match load. Our quest then is to determine the total voltage, V1 and V2, the two port plane voltages now. And since we've replaced the transmission line with a matched source and the transmission line over here with a matched load, what we have is a circuit that looks very much like we might have encountered our freshman year in circuits class. And we could analyze this readily using the techniques that we learned in that class. For example, we could combine this resistance Z0 with this resistance 2Z0 there in parallel, combine them together to make one resistor, and then use voltage division to find this voltage V1. And that's what we do here. So here's the voltage. The combined resistances in parallel turn out to be a value of 2/3 Z0. So we insert that result into our voltage division equation, and we find that the total voltage V1 is equal to 2/5 VG. So the result is in terms of that open circuit voltage VG on our matched source, and that is always going to be the case, that these voltages are going to be dependent on whatever that value is. We can then turn toward the second port voltage V2, but we look at that circuit and we can tell by KVL that V2 is simply equal to V1. They're in parallel with each other. And so V2 is likewise equal to 0.4 VG. So since we have a matched load at port 2, the incident wave on port 2 is equal to 0, and therefore, we've talked about earlier, the scattered wave at port 2 is simply, the scatter wave voltage at port 2 is simply equal to the total voltage at port 2. And again, that's because the incident wave voltage is equal to 0. The total is the sum of the scattered and incident. If the incident is 0, then the total is simply equal to the scattered, and vice versa. And so we find that our scatter wave voltage, when evaluated at the port plane of port 2, is simply, again, 0.4 Vg. Now, how do we take that and determine our first scattering parameter of S21? We know that the minus wave voltage is equal to the total voltage at port 2. Now, here's where students go wrong oftentimes. Well, gee, if the minus wave, the voltage in the numerator here is equal to V2, then the voltage in the denominator must be equal to V1. And so students will say that the plus wave voltage is equal to the total voltage V1 because, gosh, the minus wave voltage was equal to the total voltage V2. The minus wave voltage is equal to the total voltage V2, as we found, but of course the incident voltage at wave voltage at port 1 is not equal to the total voltage. Actually, if that were true, this would be 1, would be the value that what students would give me. Sometimes students will make this value not V1 but VG. They'll take the total voltage V2 and divide by VG, and in that case you would get 2/5. Both of those are incorrect. All right, this is completely bogus. The value of S21 is not equal to 1. It's not equal to 2/5. We have to carefully go through and figure out what is the incident wave for this particular problem at port 1. So the key thing to keep in mind here is we put a matched source at port 1, so the incident wave is not 0 at port 1. It is at port 2, but not here at port 1. This is the engine. This is what's supplying energy into our circuit. The incident wave is carrying energy along with it into our circuit. So the scattered wave at port 1 is the difference between the total voltage, the port voltage V1, minus this incident voltage. And again, this is the problem that students have. We can calculate readily using voltage division the total voltage V1, the port voltage V1, but we need to parse that into two components, one being the scattered wave voltage at port 1 and the other being the incident wave at port 1. We know the total voltage. What is the incident voltage? And of course, that's the great thing about using a matched source to do the experiment for finding the scattering parameters. For a matched source, we know if we attach a matched source to port 1, we know the value of the incident voltage at that port plane must be equal to Vg over 2. That's one of the special cases that we studied when we take a matched source and connect it to a transmission line, characteristic impedance 0. We know the voltage at the port plane of the source is going to be Vg over 2. Since the port plane of the source in our case is also the port plane of the device, port 1, we can say the incident voltage plus voltage at port 1 is simply half of Vg. So now we can determine the scattered voltage at port 1, the minus wave voltage. We take the total voltage, which we found from voltage division, and now we subtract from it Vg over 2. We get an answer here for the scattered voltage on the first port of minus Vg over 10. Once again, the answer is dependent on this open circuit voltage Vg. So now we can find our scattering parameters in the first column here. S11 is the normalized scattered wave amplitude divided by the incident wave amplitude, the normalized wave amplitude A there, and this is B, and this is the inverse of A. We now know what the minus wave voltage at the port plane is. It was the total the minus wave voltage at the port plane is. It was this value, minus 1/10 Vg. We know what the incident wave at the plus port wave at the port 1 is. That's simply 1/2 Vg, and so the square root of the z-zeros cancel out since the characteristic impedances of the same or always cancel, and so we get a minus 1/5 or minus 0.2. S21, again, we take the ratio of normalized wave impedances, incident for A, scattered for B, and we know what V2 minus is. That's simply equal to the total voltage at port 2. Again, the plus wave voltage at port 1 is again 1/2 Vg. Take the dual algebra, VG's cancel out, we get 4.5. And so we get an answer here that is independent of VG. The VG cancel out, and that has to happen. If it doesn't, you've made a mistake. These results, of course, are the same results as we did when we applied boundary conditions. Any valid method will give you the same answer. All right, so that was just one experiment we did. We put an incident wave on port 1 and found the first column of our scattering matrix, S11 and S21. To complete the scattering matrix, we would need to go through and put a source on port 2 that would generate a non-zero incident wave, terminate port 1 now at a match load, and then go through and repeat the process we just did, and from that get the scattering parameters S12 and S22. So you could argue we're only halfway done. We have to go through and do it all over again. This becomes particularly painful when this is a 2-port device. It becomes particularly painful if we had a 4-port device, because we have to do 4 experiments, 4 different analysis with sources at 4 different ports or incident waves at 4 different ports. But if we're smart, we can evaluate the symmetry of our circuit and determine exactly how many of those scattering parameters we really need to determine. It turns out in this case, because of symmetry, we're really done. There's no more values we need to find. S11 and S21 are sufficient to determine the remaining 2 scattering parameters. So we look at our circuit structure here, and we see we have a plane of bilateral symmetry. The characteristic impedances are the same on both sides. If we rotate this around 2Z0, it remains the same resistor 2Z0. Basically, we're doing a permutation where we take port 1 to 2 and 2 to 1, and we have exactly the same circuit as we have before. This is a circuit with D sub 1 symmetry, a group of order 2, one being the identity, and the other, of course, that reflection. 1 goes to 2, 2 goes to 1. And we studied that in the circuit symmetry case, and we know that this symmetry will manifest itself in our scattering matrix. So we go back and look, and we find, and of course you can make 6 symmetry arguments without even looking, to argue that S11 and S22 are going to be equal to each other because of the symmetry of the operation. 1 goes to 2, 2 goes to 1, so S11, 1 goes to 2, 1 goes to 2, we get S22. S11, S22 are the same, and again, that should be evident when you look at the circuit because of the symmetry. S21, therefore, is equal to S12, and therefore we can determine the second parameter, S12, as 4/5, equal to the value of S21. Once we have the first row done, we can immediately write the second row of that scattering matrix because of symmetry. So again, make sure that you look at that. Notice the other result, or the second result here, is likewise true due to reciprocity. So even if it weren't symmetric, we could make this argument due to reciprocity that S21 and S12 should be the same. So we look at the scattering matrix that results from this device. Now, if we were to go through and look at the magnitude of each of these columns, what we'd find is they were less than 1. If we take the inner product of each column with itself, the Hermitian transpose, we would get a 1 over 25 plus 16 over 25. So that would be 17 over 25. Well, that's a number less than 1, of course, but this doesn't concern us. All that tells us is the matrix is not unitary. In other words, it tells us that the device is a lossy device. And of course, the device consists of one element, which is a resistor value 2Z0. And a resistor, of course, will absorb energy. So if it turned out to be a unitary matrix, then it would give us concern because that could not happen. But this verifies, if we did not already know it, that this device is lossy. So that's one thing we can look at. Again, we look at the scattering matrix here, and if we only do the scattering matrix, we could determine a lot of things from this device. We could determine it was not matched. It's not a matched device. Otherwise, S11 and S22 would be equal to each other, or equal to 0, rather. We could see that it is symmetric. The level of symmetry would have a D1 symmetry, and we could tell that it is a lossy device.